Congratulations to you guys, you have made till now, and I welcome you all to the very first machine learning lecture. And in this particular lecture, we'll be dealing with the first machine learning model that we have in our course, that is a linear regression model. It is basically a regression model, and it's a very basic model to understand. In this lecture, we'll be understanding what linear regression model is, how it functions, and what are different components involved in training a machine learning model. Okay, so let's move on. So suppose we are given this data x and y, where this x is the input value and y is the output value. These and xy could be any. For example, this is the experience of an employee and this y is the corresponding salary. Although there are many components in predicting the salary of an employee, let's just take an example that we have only two parameters, one is input and one is output. Right, so we feed in this particular data to our linear regression model, and our linear regression model will predict this y value based on this x value. Right, you can have different input values also, but linear regression model can only work on a linear hypothesis, that is a single degree hypothesis. What I mean to say is, I'll show you in the coming time, don't worry about it. Okay, so let's move on. So hypothesis, this is the most important thing when we are dealing with a machine learning model. Each machine learning model has a hypothesis, using that it predicts the value, and in case of linear regression we have y equals to mx plus c. Right, let's treat it as a y predict value. Okay, and this x is the input and this y is the output. So this is the input and this is the output. Now most of you must be wondering that it is a simple line equation, mx plus c. So yes, you are thinking right, this is a simple line equation. A linear regression model work on a very simple hypothesis, mx plus c. So after training a machine learning model, this y equals to mx plus c will be our final hypothesis. Initially, before training our model, we have only input values, right? We don't know about m and c, so we train our model. By training, what I mean to say is, we have to find the most optimal values of m and c, so that after training our model we have this final hypothesis y equals to mx plus c, and using this mx plus c we feed in x values, and m and c will be the optimal values we have already find out after training, and feeding the input values x we can predict this y value. Okay, what I mean to say is, suppose this is x and this is y. Now mx plus c, m means the slope, right, and c here means the y intercept, right? So once after training the model, you will have your final hypothesis. Let's say this is your hypothesis. Okay, and you are given these x values in your data. So using this hypothesis you can easily predict the y value. How? You can simply enter x in your hypothesis, so mx plus c, so entering, so corresponding to this x value we have this y value, corresponding to this x value we have this y value, corresponding to this x value we have this y value. Okay, so these will be the predicted values of y. So this is how a linear regression model works. You train your model to let it have the final hypothesis with the most optimal values of m and c, and using this mx plus c you predict your values. Now the question arises, what I mean to say by optimal value, right? You could have any values of m and c, but what it means to have optimal values of m and c. Initially, okay, wait, let's understand cost function first. So you are having your hypothesis y equals to mx plus c, right? Initially when we start training our model, we have this input value, right? We give any random values to m and c. Okay, and then our model will calculate our model will use those random values of m and c, and the input we have passed, and the model will predict this y value, right? But we have to calculate the cost. So cost is equals to 1 upon 2n, where n is the total number of data entries we have, y predicted minus y whole raised to the power of 2, and it will be summation I equals to 0 to n, that is total number of data entries. So this is how we calculate the cost, or you can say error, of our linear regression model. Okay, so suppose initially you are given x and y values. I have told you that when you train your model, your model knows about x and y values, and at the time of testing your model, you will pass on x value, it will give you some y predicted value, and then you will compare this value. Okay, let it be x train, y train, this is x test. This x test values won't be seen by our model when it is training. At the time of training, it has seen these two data components only. This component, when we feed in for testing, it will predict some y predicted value, and then we will test this, we will compare this y predicted value with the actual value, that is y test value corresponding to these x test values, right? And we say that our model is this much accurate. Okay, so suppose initially we have x train and y train, so let's mark the points. Okay, now let's say these are the training data points we have given to our linear regression model, and we have initialized m and c randomly. So suppose this is our hypothesis line, right? Now calculate the distance of these points from this data. It has 0 distance. Okay, so now these points on this line will be the y predicted value of our model. Okay, so we will compare the distance of this particular value, or sorry, we apply this cost function on these points. These points were the actual y test values, y train values, and this is the predicted hypothesis. So based on this, our model will find out a cost value. Okay, let's say the cost value is 100 or any value. Now our target, by training, what I mean to say is that initially we have randomly given m and c values, but when we keep on training our model, this hypothesis will fix to a position, say this, okay, where we have the most optimal values of m and c. And by most optimal value, I mean to say that the more lesser the cost will be, the better the performance of our linear regression will be. So our target is to decrease this cost value and to accurately predict the value. Our target is to find out a hypothesis value or a best fit line, so that the distance between our predicted value and the actual output will be least, so that we could predict the value of our input very accurately, right? So this is how a linear regression model works. It has a hypothesis, we given it m and c values randomly, it finds the cost function, and we have to reduce this cost functions by again updating this m and c value. Now the question arises, how to update these m and c values? And to update this m and c value, we have a very important thing to understand, which is gradient descent algorithm. And we will understand the concept of gradient descent algorithm in the next coming lectures. Okay, so first of all, we have we perform forward propagation, then we calculate the cost. Now our target is to reduce the cost, right? So suppose this is a cost function, and initially we have this much cost. Our target is to reduce this cost value, right? So what we want is we perform the gradient descent algorithm, and we descend to this particular function till we reach it over to this point where we have the least value of cost function, right? But doing so, there is a very important parameter involved, that is alpha. This is the learning rate in case of a gradient descent algorithm. If alpha is too high, then what will happen is we can directly jump over here, then it will go over here, then it will go to here, then it come back, then it will keep on moving and won't reach to the optimal value so easily, right? There is one more case, that if we have a very small alpha, right? So let's say this is our cost function, and if we have very small value of alpha, then what will happen is, this is our cost function, it will come over here, come over here, come. So it will take a huge time to reach to the optimal cost function value. So we need to choose this alpha very carefully so as to reach and reduce our cost function efficiently, right? Now let's understand how the gradient descent and backpropagation works. So we have our function y equals to mx plus c, and we want the most optimal values of m and c. But how? For that, what we need to do is we find a new values of m. After we calculate the cost, we reduced the c values. So let me show you here. We update the parameter new m equals to m minus, that is the old value of m, minus alpha del cost by del m. So this basically is the backward propagation. We are reducing cost with respect to m, right? So which is equals to m minus alpha 1 by 2n, because we are differentiating by m, so there is no need to do with anything with n, so we take it out, and now we have inside y predicted minus y raised to the power 2 by del m, right? Now this 2 and this 2 will come out, this 2 will come out, and this 2 will cancel out. Okay, so we will be having m minus alpha by n. Now this y and on differentiating, it will 2 will come out, it will be y predicted minus y, and again differentiating this y predicted minus y with respect to m. Now y predicted equals to mx plus c minus y, right, by del m. Okay, so it is equals to m minus alpha by n, y predicted minus y, and when we differentiate this particular function with respect to m, this will cancel out, this will cancel out, and we will left with x only, right? So this is the final value of our new m value. So new m value will be equals to m minus alpha by n, y predicted minus y into x. Okay, and similarly for c, new c equals to c minus alpha del cost by del c, and which is equals to, okay, this step will remain same, and now directly I'm writing alpha by n, y predicted minus y del mx plus c minus y with respect to del c. And now when we differentiate this function with respect to c, this will cancel out, this will cancel out, and del c by del c equals to 1. So we will left with c minus alpha by n, y predicted minus y into 1. So this is our new value for c. Okay, so this is how we find the values. Okay, now after finding these values, we update our parameters. So m dash equals to the value we have, that is old value, minus alpha by n, result of backpropagation, right? So this is the final m value, this is the final c value, c minus alpha by n, y predicted minus y into 1. Okay, so what happens is, basically we have forward propagation where we solve y predicted equals to mx plus c, right? Then after finding this y predicted value, we compare it with the actual value and we find the cost. which is equals to summation I equals to 0 to, that is total number of points n, 1 by 2n, y predicted minus y raised to the power 2. Now we want the least value for cost. We want to reduce it as possible. So for reducing it, we do backward propagation and we use gradient descent, where we find del cost with respect to del m and we find del cost with respect to del c. And then using this result, we update our parameters, and which is equals to this, right? And now we will again use these parameters in this particular equation, and the entire step will keep on continuing. These iterations will keep on working on till the number of iterations where we find the most optimal values of m and c. And once we have found the most optimal values of m and c, our hypothesis mx plus c is ready, and we can feed in any values to our model and it will predict a output value for it. So this is how the linear regression model works. This was all the maths behind linear regression model. So let's begin with our lecture, and I'll be loading the basic libraries pandas, numpy and matplotlib. Okay, so import pandas as pd, import numpy as np, and import matplotlib dot pyplot as plt, import matplotlib dot x's as x. Okay, and now we'll load our data. So data equals to pd dot read csv, and then our data is named as train.csv. Okay, let's check the data. So data dot head, printing the first 10 values. So these are the values. This x is the input and y is the output, as I have already told you in the intuition videos. Let's check the data information. So you can see that x has 700 entries. So we have 700 entries for the input, but 699 entries for y. That means we have a null value in our data set. So to handle the null value, what we'll do is we simply drop the data entry where we have null values, and this won't be creating much effect on the data set because we have only one entries with the null value. Okay, so to do so, we'll simply do is data equals to data dot drop na, and since we want to remove only the entry with the null value, we mention x is equals to 0. That means we want to remove that particular row only. So let's check the shape of our data also. Data dot shape. Okay, so now you can see we have 699 entries with 2 columns. Okay, let's check the info also. Data dot info. So you can see now we have x and y pairs both having 699 entries. Okay, now we split our data because we have to train our model and test our model. So we have to split our input and output as training input, training output, testing input and testing output. Okay, so let's split it as train input, train output equals to. Okay, so let's split. So what I'm doing is I'm putting first 500 entries to the training part and the remaining 199 entries to the testing part. So what I'll do is I'll say np.array and data, which column, x column, and I want first 500 entries, right? And since we want it to be in the shape of a column, so we'll reshape it as 500 entries with 1 column, right? Similarly, we'll do the same stuff with our train output. just we need to make the change in the column. So for that we have our Y column. Similarly, we'll prepare the test input and the test output. Okay, so here we have our values. Let's copy it again. Now, copying it again, and now we will tell that we want the remaining values. So from 500 till 700, not considering the 700th entry, right? So we have total of 199 values over here. Let's again copy it and changing the column. Okay, so here we go. Now we have 4 components as we have discussed in the data splitting video, intuition video, right? So let's check the shape of our data. So train input dot shape, train output dot shape. Similarly for test input dot shape, test input dot shape, and test output dot shape. So here we go, we have train input and corresponding train output. We have test output which our machine learning model will predict, and the predicted values will be compared with this test input values. So this was the basic stuff to handle the data. And now in the linear regression we have 4 components, that is forward propagation, cost function, backward propagation, and updating the parameters. And we were discussing about the components of linear regression model. So in this lecture we'll be talking about forward propagation. Forward propagation means the hypothesis that we have, so that is equals to mx plus c. So we have to predict our values using this mx plus c only. So let's code this. So for that I'll be creating a function named as forward propagation, right? And for forward propagating, what values we want? We want our input values x and m and c. So input is train input, and the m and c values are present in the parameter. Okay, so the parameter list will have our m and c values. So m equals to, don't worry, when we'll be using all these functions together, we'll be creating a parameter list over there. So parameter column m, and similarly c equals to parameters, c, and the y predicted value will be predictions equals to, now it is mx plus c, so we'll say np dot multiply m and the train input values, that is x, plus c, and return the predictions, right? So this is all in forward propagation. We have basically built up the hypothesis y equals to mx plus c. So basically cost function was equals to 1 by 2n, where n is the total number of entries we have, that is 699 in our case right now, and this y is the y predicted value, and this y is the actual output value, all raised to the power of 2. So we'll code it. So for that I'll be preparing a function, and let's name it as cost function only. For that what we need is the predictions and the actual train output value, right? So the cost will be equals to np dot mean, because we have n number of entries, so it will automatically do upon n. Okay, and what we need to pass is train output, or you can say predictions Anyway, it is all correct because we are scaling this value, right? Scaling this value, dividing by 2, so into 0.5. So this is our cost value, and returning this cost value again, right? So this is our cost function. We have implemented 1 by 2n predictions minus actual training output raised to the power of 2. So this was all cost function, and in the next coming lecture we'll be understanding the gradient descent for backpropagation. Okay, how we can hard code our gradient descent algorithm for backpropagating the values. Okay, so first of all, understand this. When we are updating our values, so the new value will be equals to m minus alpha by n del cost by del m, right? So when differentiating our cost by m and differentiating our cost by theta, this will be our new value. So m dash will be equals to m minus alpha into dm, and theta dash equals to theta minus alpha into d theta. And d cost by d, now in this particular lecture we'll be implementing this differentiation of cost with respect to m and differentiation of cost with respect to theta, that is backpropagation. And we will follow the chain rule. So del cost by del m equals to del cost by del f, that is the hypothesis function, into del f by del m, and same way we can do with the theta. Now see this one. When we are differentiating del cost by with respect to m, this will be the case. Cost is equals to 1 by 2n y predicted minus y raised to the power 2n, right? So we are differentiating with respect to m, so this 2n will come out, and now we have this particular value in it. Now differentiating it with respect to m, y predicted equals to mx plus c. So when we will differentiate it, this c and y will become 0, and differentiating mx with respect to m, we get x, right? So the final differentiation of this del cost by del f is equals to del f into x, right? And similarly, when we are differentiating with respect to theta, mx plus c, theta is c, so we get 1 over here. So we are trying to implement this only in our code. Okay, so this is a cost, so d cost by dm equals to d cost by df into df by dm. Similarly, d cost by dc equals to d cost by df into df by dc. So d cost by df equals to f minus y, right? And df by dm equals to x, df by dc equals to 1. So we will be implementing this only in our code. So for that, let's name it as backpropagation. So def backward propagation, right? And now what values it want is train input, because here we have y equals to mx plus c, so it is required. Then train output, then the predictions, right? Because df by dm equals to x, so we require train input, then we require train output and predictions, because we have to implement y predicted minus y raised to the power of 2. So these three parameters we pass onto this function, and now we have, let's name derivatives equals to, okay, and now we have to implement df. So df is equals to train input minus df is simply d cost by df, right? So d cost by df, I have named it as df only. So you can see that we have df over here. This is equals to y predicted minus y, right? This y predicted minus y, I have named it y predicted minus y by n. I've named it as del phi, right? So we will implement this only over here. So it is equals to predictions minus test output, right? So let me show you again. When we are differentiating this particular cost by with respect to f, we are finally having this value y predicted minus y by n. This y predicted minus y, I am solving it over here, and division by n I'll do moving on. Okay, so df equals to predictions minus test output. Similarly, dm equals to, now dm equals to df into x, and dc will be equals to, what I'm doing is I am finally doing this stuff. Okay, so what I'm doing is I'm saying m minus alpha into dm, right? M minus alpha into dm, and dm is equals to del f into x. So I'll be multiplying it, np dot multiply df, right, and the train input. Now it was having division by n, so what we'll do is I'll simply say np dot mean, right? Similarly dc, so let's look it over here. So dc equals to del f, that is y predicted minus y by n, so we have to divide it by n, and it was equals to 1. So what we'll do is we'll simply do this y predicted minus y by n, right? So for that we'll simply do np dot mean of df. Okay, and now we will add it to derivatives, because we will be needing these values in the further components. Derivatives dm equals to dm. Okay, derivatives dc equals to dc. You can ignore this particular column. Okay, just focus on the explanation I'm giving you over here, because you can get confused otherwise. Derivatives. Okay, so let me show you once again. What I'm doing is I'm preparing df, dm and dc, right? So df is equals to this y predicted minus y, and then this is y predicted minus y upon n, so df equals to y predicted minus y, and then dm is equals to df by n into x. So this is I have done over here. So what I am doing is, this is df y predicted minus y, this is dm y predicted minus y divided by n into x, and this is dc, which is y predicted minus y divided by n into 1, and I am putting all these derivatives to the dictionary derivatives, because I'll be needing these derivatives in the further components also. Learning about the last component, that is updating the parameters, and finally we'll be training and testing our machine learning model. Okay, so updating the parameters means, after performing the gradient descent, what we have to do is we have to finally perform the new parameter values. So new parameter value will be old parameter minus alpha into dm, and theta dash equals to theta minus alpha into d theta, where theta is c. Okay, so for doing so, we'll be making a function named as update parameters, and we need the values parameters, right? The old values m and c, then derivatives, that is dm and dc, and then the learning rate alpha, right? So here we go. Now parameter, now we have to update the parameters, right? So parameters m equals to, copying this again, old parameter value minus learning rate into derivatives, and in derivatives what we want is dm over here, right? So this is how we update our m value. Similarly, we can update our c values. So c equals to m minus learning rate into DC, and then we pass on the parameter for further iteration. Return parameters. Okay, so we are done with our components, and now it's time to train our model. What we have done is we have performed forward propagation, cost function, backward propagation, update our parameters, and again the cycle keeps on rotating. After updating the parameters, now we have new values for MNC. Now again the forward propagation will work using that particular MNC values, and we calculate the cost function, and we will try to reduce that cost function, and by reducing so we find a new optimal value for MNC, and this is how we keep on iterating till a fixed number of iterations. So now we are preparing that particular train function so that we can train our model. So let's name it as train function. Okay, so for training I have told you we need only the input components. So train input, train output, learning rate, and the number of iterations we want. Okay, so our parameters we have to declare over here. Parameters equals to dictionary. Okay, and now parameter m, we have to randomly initialize our MNC values so as to start our hypothesis value. So m equals to np dot random dot uniform in the range 0 to 1 into -1, let's say, and similarly we'll be finding our C values. So both M and C are randomly initialized, right? And what I'll do is I also have to plot a figure. So okay, wait, now we have MNC values with us and we will perform the iterations. So for I in range of iterations, right? So first prediction, y equals to mx plus c. So for that we use forward propagation. Okay, so train input and the parameters. So we pass m, x and c values. So parameters have m and c values and train input is x, right? So now we have predicted our values, y equals to mx plus c. Now we find the cost using the cost function, and for finding the cost what we need is predictions, and we will comparing it with the actual output, which is train output over here, right? And based on this cost we need to reduce this cost. Okay, so I'm storing this cost in a list append. Let's make a list over here, loss equals to list. So I am preparing a list named as loss, right? And I am appending all these cost values over here so that we can check the reduced cost. Okay, so now we have predicted our values, we have calculated our cost, right? And then we will update, we will back propagate, and for that we will use backward propagation method, and for that is the gradient descent. For that we need to give train input, train output, because we have to differentiate it there with respect to cost, and we have to multiply x also. So train input, train output, and the predictions, and the predictions, right? And after updating our parameter, after finding the new optimal values of m, after performing the gradient descent algorithm, we have to find the new values of m and c, and for that we need to perform the update parameters. So parameters equals to update parameter, and we pass on the parameters we have. So parameters, initial parameters, that is m and c, then derivatives dm and dc, and then the learning rate. right? So, and then we will finally return the parameters, final MNC value and the final cost function value. So what I'm thinking is we can plot it also so that you can easily see by yourself how the linear regression model works. So for that I'm initializing the plt.figure. Okay, you can see how the cost hypothesis is keep on rotating. So initializing it, so let's say fig comma x equals to plt dot subplot, because we are creating more number of plots at each iteration. Ax dot plot train input comma train output. That's the actual hypothesis. Let it be marked by plus and label equals to original, right? And similarly for the hypothesis that our model is predicting, so train input and the predictions, okay, and comma, and it's the training of our model, right? Then legend equals to AS dot legend, and then we'll be using this legend when we are plotting our values. So plt dot plot train input train output with a plus and plt dot plot with star and plt dot show. Okay, so I think we are good to go. Let's check the code. Okay, yep. Now let's run it basically. So it's passing on two values, parameters and loss. So we are storing it in these variables. So train, and then pass on our values, train input, train output. Let our learning rate be 0.001 and iterations be 20. Okay, it's giving some error. So here we go. Now at iteration first, this was our actual hypothesis. This is the hypothesis that is randomly initialized. Now our model will learn. Okay, wait, it's giving error again. Predictions. Okay, I have done a spelling mistake over there. Right. So let's run our code. So now our code is running. So now at iteration first, this was our actual hypothesis. This was our actual values, and this was the hypothesis that we have randomly initialized with MNC values. Now as our model keep on learning, this MNC values are updating. Now you can see that it is coming closer and closer. Model is updating. Now also look at the cost value. Initially it was around 3897, then it reduced to 1770, reduced to 805, reduced to 367, 168. As it is coming closer and closer, so the distance between these data points is getting reduced. So the cost function value is keep on reducing again and again, and the model is getting trained. It is coming over the actual hypothesis. Now you can see in the final iteration, that is iteration number 20, that this hypothesis is lying exactly on our actual input values. So with the loss of 3.96, we are predicting the value. So this is our hypothesis value we are finding, right? So this hypothesis has the most optimal values of M and C. And now using this hypothesis value, we will predict our model. Okay, so let's check the parameters we have. Parameters. right? So this is our final C value, this is our final M value, right? And now we will predict our values using this particular function only. So let's name it as test predictions equals to test input, test input mx plus c, right? So this is, now we are predicting our test values. So test input into m, so which is stored in parameters m and c, parameters c, right? So this is y predict equals to mx plus c, plt dot figure, and we'll be plotting. Let's copy this code from here only. Okay, plt dot plot, and now we have test input values over here, right? Because we are predicting test input now. So test input with respect to test output, that is the actual value with respect to the test predictions, right? So let's run our code and see how it has worked. Okay, test predictions, let's do it. Yeah, so now you can see these plus values were the actual values and this star values are the hypothesis model we have. Now let's check the accuracy of our method. So let's calculate the cost function passing on these values, test predictions and the actual test output. So now our machine learning model has predicted the values with an accuracy of around 96%, which is very amazing because we have a very simple data and we have successfully trained our machine learning model, that is the linear regression model we are using over here. We have predicted the test output values for our output values, right? So we have passed on these values, we have predicted these test prediction values, and we have compared these values with the actual test output. You need not to hard code everything in linear regression. You can just use a linear regression function from Scikit-learn library and it will be very easy to implement this particular model. So let's begin with our lecture. First of all, we'll import our libraries. Okay, so for that I'm importing NumPy, Pandas, Matplotlib. Okay, so here we go. Now we'll import our data. The data which we are using in this lecture is named as datafile.csv. Okay, so this is our data. This X column is our input and this Y column is our output, right? And we have to reach to the hypothesis y equals to mx plus c, where we'll be predicting this Y value. Our model will get trained to find the best values of m and c, and it will predict a Y value, right? And then we'll be comparing that particular Y value which our model has predicted using the equation mx plus c, and we will compare that particular Y value with the actual output value. And this is how we train our models. We perform the gradient descent, update our m and c value, and after performing all the iterations, we'll be reaching to a fixed value of m and c, and using that equation, we'll predict our values. So let's see what I'm talking about. Okay, so let's load our data. So data equals to, for that we'll use read.csv, pd.read.csv, right? And then we have to mention the path of our file. Our file is named as data file, and I'll give the path. Okay, so users. So yeah, we have loaded our data. Now let's just check what our data looks like. So data.head. So this is our data. This is a particular data we are using. We have input as X and output as Y. Let's check the data info also. Okay, so now you can see that in X column it's showing that we have 700 entries, and in Y column it's showing that we have 699 entries, but in total we have around 700 entries. That clearly means that we have a null value in case of this particular Y column, right? So we don't want to feed this kind of data to our machine learning model, so we need to pre-process our data. So for that, what we need to do is we need to handle this null value. Okay, so to handle this null value, what I'm using is I'm simply using drop NA function, because we can afford to drop a single entry from our data. It won't make any difference in the training of our model. So for that, what I'll do is I'll say data equals to the initial data dot drop NA. I want to drop my null value, right? And I just leave it like this only. We need not to mention the argument because we don't want our columns to be deleted. By default, the argument is delete the row, right? So let's check. So now we have dropped. Let's again check the data info. Okay. So here we go. You can see now that we have 699 entries, and both the columns have same number of entries. Now there is no null value present in any of the entry. Let's check the data shape also. You can also check this from over here. So now you can, sorry, it will give an error. So now we have 699 entries and 2 columns. That is an input and an output column. So now our data is ready to go with it, and now we'll split our data to training and testing parts. That is training input, training output, testing input and testing output. So for splitting my data, what I'm doing is, let's say train output, train input. Okay, so for that I'll be making a numpy array out of my data because I'm slicing my data. Okay, so data, which column? X column. And let's say I want first 500 entries for the training. So we'll mention it like this. So we have sliced our data and we are saying that yes, we want first 500 values in the X column as a training data. Okay, and since I have used a reshape array function, so we have to reshape our data also. So we'll reshape like this, 500 comma 1. That means I want 500 rows, 500 entries all in a single column as we have in our data frame, right? So this is how we make our data. So I have given first 500 entries to the training input, and similarly I'll do the same thing with my training output, but here just a single change is that we now access our Y column because that's our output value. So I'm saying that I want my first 500 entries of output column in train output value. So now we have corresponding XY pairs for the training of our models. Similarly, I'll be creating the training output test input and the test output values. So for that you just copy the same code. Okay, but now the difference is I have taken first 5 entries for the input, and now I want to say that okay, let's take the rest of the entries for testing input, testing output. So for that I have to say 5 from 500 till 69, so 699. So I have to mention 700 over here, and the total number of entries here is 199. So we have to change this reshape also. Okay, and similarly we'll prepare the test output where we'll be testing our model later on when we will predict any value. So np.array data, let's copy this same code. So here we go, and we have to make a simple change that now we'll be accessing Y column. Okay, it's giving an error. Yeah, so we have now splitted our data into training input, training output, testing input and testing output. And let's check the shape of our data. You can do so by using your data name dot shape simply. So we have 500 entries in training and 199 entries in the output data. Okay, so now we have our data ready, and we'll be now using linear regression model from the Scikit-learn library. We will not be explicitly preparing the functions for gradient descent, cost function, forward propagation, backward propagation. All this stuff will be carried out by this particular function only, which will be importing from Scikit-learn. Okay, so what we'll do is from sklearn dot linear regression. Okay, so we want linear regression model, and we'll be importing it from linear model, which is a part of Scikit-learn library. And now we'll be importing our linear regression module. Okay, so linear regression, right? And now what I'll do is I initialize this linear regression model. Okay, so what I'll do is I'll say linear regressor. You can name it accordingly, whatever you want. Okay, right. And now let's initialize our linear regression model. So for that I'll say so now it's being loaded, so just wait for it. So now our model has been initialized, and now what we'll do, we'll train our model. And for that there is a very simple function, that is a fit function. So we need not to do any big task. We'll simply use linear regressor. Okay, we want our linear regression model and we want to train it. So for training we use fit function, that yes, train our model. And for training we have to use the train input and train output value, right? So we'll just copy it. So this is our input and this is our output. So here all the gradient descent, cost function updation, back propagation, forward propagation, updating the parameters, this all stuff will go over here and our model will get trained, right? Let me first show you that what our regressor is. Let's print it also so you can see. Okay, so this is the basic arguments which are already by default in our linear regression model, right? So now we are training our model. So it's training right now. So yeah, we are done with our training part. Okay, our model has been trained according to the train input and train output. Okay, so now it's time to test our model, but for that we have to predict some values and then we'll be comparing it with the actual test output, right? Our model doesn't know anything about our testing input and testing output, so we'll be feeding our model testing input now, and using that input values it will predict some value. We have not shown the testing output to our models, and when the model will predict, we'll be comparing that predicted value with the testing output. So for that, let's name it as predicted value. Okay, so predicted value equals to, now this is our model linear regressor. So linear regressor dot predict. It's very easy. So now we want to predict, so we'll use the predict function. What we want to predict? We want to predict the test input values, right? So we'll pass our input to the model and our model will predict some values. So here the model has predicted some value. So these are the predicted values by our model. Okay, so these are the values, right? And now we'll be comparing these values with the test output values. Our model has not been shown this test output value, so now we'll be comparing this value. You can see that our model has predicted 4 and it's actually 7 over here, then it's predicted 60 and it's 61 over here. So that's the error we are talking about. It is not 100% accurate. We have to check the performance of our model. So for testing the model. So for checking the performance of our model, we again use the Scikit-learn library. So for that, we'll be again using Scikit-learn library. So from sklearn dot metrics, I'll import mean squared error function. Import mean squared error, right? So now I'll be calculating the mean squared error using this predicted value and test output, right? So we'll be comparing these two. So let's name it as error, and mean squared error will pass the argument values, that is input to this function. So it is test output and the predicted values, right? So our model will compare these two values, predicted value. Okay, so now we have given this test output and predicted value to our mean squared error function, and this particular function will calculate the mean squared error between these two values. Okay, so let's print it. So error. So you can see that we are getting just about 8% of error, and our model has predicted these predicted values with an accuracy of around 92%. You must be thinking that this is very less accuracy, but with respect to this particular lecture, we are using a very basic model, and the dataset we are working on is very simple. We have just one parameter to predict a value. But when we'll be working on a real world data set, then it will have lots of parameters with correlation in between them. So let's visualize our model also, how this model has performed. Okay, this is the error, that's 8.03%, which means that the accuracy is around 92%, which is good. And now we'll be visualizing our model's performance. Okay, so for that, what I'll do is I'll plot my original hypothesis. Okay, so original hypothesis as well as the hypothesis which my model has predicted me. So let's name it as model hypothesis. Okay, so let's plot it. plt.plot. Now we have to pass the input and output value. So the input value is test input, right? And the output is, since it is the original hypothesis, I'll be plotting the actual output values. So that was test output, right? And let the color, first I have to mark the symbol. So for that, let it be star and the color be green. Okay, so green. Similarly, what we'll do is we'll copy this code. We'll say test input versus the predicted output. So predicted value, and let it mark with plus and color be red. Okay, and let's label our axis. X label equals to input y label be output. Okay, and then plt dot show. So yeah, here's our model performance. This particular green line is the actual original hypothesis, which is the actual value for our test output, test input, and this red one is the predicted value. These are the predicted values which our model has predicted for the test input, right? So this is how the model works. You can clearly see that it's almost completely overlying over the actual hypothesis, but it's giving some errors. This is because, suppose in case of this particular value, this star value and this plus value, there is an error, right? So it has plotted this particular line, this red line, based on the final values of M and C, and it's predicting it with an accuracy of 92%, right? So this is how actually our models work and we predict the values. So this was all for this lecture. And just keep one thing in mind, that whenever you are studying a machine learning model, the basic fundamentals is that you first learn the maths about it, right? So in this particular series, we have told you about the maths that is behind this working of linear regression model. Also, we have worked that how we can code our linear regression models from scratch, and also how we can use Scikit-learn library to make our task much more easy. And this was all for this lecture. Best of luck. Keep following.